This is Oscar Ocampo, and I did my at-home lab of the solar system. So the question was, can one accurately predict the length of a day or a year from the Python model? So the equation that we'll be using in this lab is the gravitational force, because that's the only force that will be present in the interaction of the planets, which is just the gravitational constant times the mass of the sun times the mass of the planet and the radius squared. This radius is actually the distance from the sun to that other planet, and this is just the position of the radius, so r hat. Now, as I mentioned earlier, the F net will just be F grav, because that's the only force that will be present during this whole production of my code. Now, the equations that we'll be using is, first one is the momentum principle, which is the final momentum equals the initial momentum plus F net delta t. Why we will use this is because we'll need to calculate the final velocity. Because the final velocity, you just take that by dividing the mass on all sides, so you get V final is equal to V initial plus F net divided by the mass of the planet times delta t. And using this, we use the update position formula, which is just R final is equal to R initial plus V average delta t. This will give us actually that elliptical orbit that is present in the code. And then this V average is actually the final velocity calculated through the momentum principle, because the delta t that will be chosen is so small that you can actually neglect the average of between the final and the initial and just make the final your V average. Now, if we go back to the code, we had to establish a couple of things. The first is the gravitational constant, which is 6.7 e to the negative 11th. The delta t, which I chose to be large because the code would run too slow if it wasn't this big. And then we found the actual how much each mass weighed in accordance to the online stuff. And then we just basically took, multiply the mass of the Earth with Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune in accordance to the scaling. So, like, for instance, Venus was 0.815 times the actual mass of the Earth. Now, here is where we establish the positions for Mercury, Venus, Earth, and Mars in the X coordinate system in accordance to the actual Sun. And these are all the radiuses. And now as we go down here, we calculate the velocities, which were given to us in a data table online through t-square in the y scale. And then after that, we determine the momentums by just multiplying the masses by the velocities. Next, we established the while loop, and within one, we calculated the radius from the position of each planet to the sun. The sun was the origin. And then we calculate the magnitudes, its direction, and here is the force that we calculate for each individual one. Here we ended up the net force of the Mercury, which is just the gravitational force. And this is the momentum principle, which is P final is equal to P initial plus F net delta t. And then the velocity of Mercury is just the final momentum divided by the mass of Mercury. And here is the update position formula, which is just final position is equal to initial position plus the V final, because the delta t is small, times delta t. And when we run the code, it just looks something like this, which, as you can see, is the planets revolving around in an elliptical kind of path. Over here at the farthest end is Uranus, actually Neptune, Uranus, and so on. Now, in answer to the question of how accurate this model will present the amount of time of length of a day, a month, or year is, it's based off the fact that we're basing this off prior knowledge of how long a day, a month, and year is on the Earth. So, if in terms of this aspect, the Python model could predict accurately how long a day, month, or year is. Besides that, it is very hard to predict how long the year, month, or day is without prior knowledge. Now, the code calculated the total number of seconds it took per one revolution, which was calculated by you taking 2 pi times the actual radius between the Earth and the Sun divided by the velocity or the orbital speed of the Earth, which calculated the total number of seconds in the revolution, which was counted as a year. So that gave us the length of a year. Now, based off old knowledge, we know that a whole day is calculated by multiplying 24 hours times 60 minutes times 60 seconds, and then there's 12 months in a year. So this accurately posted that the length of a month is 30 days and 65. 30 days, 0.65, which is around the estimate of what a month is usually in a year, because a month is usually from 30 to 31 days. Now, going again the year, it calculated a total number of days of 366.635 days, which is very close to 365 days. So as you can see, based off old knowledge, then we can calculate accurately the length of a year, a month, and a day. However, if we didn't have any of this actual previous knowledge, it would be very hard to calculate the number of days, month, or year with just the information in this code.
Finished?